What you missed was the drama of Harrison standing in front of the camera. All right, so problem 31. Two children pulling on a third child on this snow saucer sled. The exerting forces F1, F2 as shown. Find the acceleration. Direction of the frictional force is unspecified. It's opposite the direction of the sum of those two. And so the kid's being pulled backwards. So 10 and 8.
I didn't understand how they got the total value. Like they got 3, but like how?
Alright, well, let's run
That's the
through.
only part I didn't understand.
45 degrees and 10 newtons, and then 8 newtons, 30 degrees. And then friction of 7.5 newtons, somewhere opposite whatever the sum of those two is. Do I have the solution sitting in front of me? That's the old book. All right, so your question is more specific. Sorry, I don't have the solution sitting in front of me.
Well.
Sorry, which one?
This one.
The 3. And they got 3.07 newtons. All right. All right. Since we're given angles relative to the dotted line right there, so we'll set up a coordinate system like that. I hat, J hat. And in order to figure out the direction of the friction force, we need to add those together. So the 10 newtons, so we break up in the decomposition phase. So this to the right will be 10 cosine of 45 degrees and 10 sine of 45 degrees. And for the other one, it's 8 cosine of 30 degrees and then down 8 sine of 30 degrees. So when we add the vectors, it's several ways of doing it, but basically we're going to add those together. They're in the same direction, so it's just, once you have those, it's straight up math. And then these are in opposite directions, so one's positive and one's negative. So 10 sine of 45 degrees is 7.07, I believe. And 8 sine of 30 degrees is 4. So we'd have 7.07 j hat minus 4 j hat. And that's where the 3.07, stick units back in.
You did minus?
Yes, because they're in opposite directions. When you're adding vectors, direction matters. So even though they had a plus sign there in the solution, you're adding a negative.
Okay.
Is that it? Okay. Other questions?
32B.
All right, so this was the car mired in the deep mud.
Yeah.
What force would you have to exert perpendicular to the center of the rope to produce a force of 12,000 newtons? So the way it's worded, the 12,000 newtons is going to be the tension in the rope. Since the force is along that line there, so if I have car, that's straight ahead, and we have a tension going off in that direction. I I know that's 12,000 newtons, and the question is, what would this force need to be to give you an angle of 7 degrees?
Yeah.
And so I'm dealing with the opposite and the hypotenuse, so a sine, so the sine of 7 degrees is equal to, let's just be clever, what, x? X over 12,000. So x would be 12,000 times the sine of 7 degrees, which is something small.
So it's basically the same as A, but you change the angle from 2 to 7.
I believe so. Yeah, my reading of that is, it's not really a different problem other than giving you something more realistic
Okay.
of what the angle would be. Somewhat related to the force bit, I was stuck in the house I was living in at the time. There was part of the driveway which was down a hill, and then you go up the hill and then down again. I was stuck in the snow and ice down lower, and I needed to get out. And there was no tree right in front of me, because physics problems, they always have some solid object right directly in front of you. Not so in my case. Or the one that was directly in front, I didn't have anything long enough to attach it. So, but there was a tree over here. And so I attached it like that, and as long as I had some component of that force in the direction in which I'm going, that's all I needed. It just needed enough to eventually reach the gravel. And it worked. Anyway, side note. A thrilling application of physics in real life. That's right. I'm seeing, although your eyes are not us all necessarily going, wow, that's cool. I know in your minds, you're all thinking it. Other questions from chapter 4?
Oh, so it said, for a lot of the problems that we have to do a free body diagram, but on the quiz, are you, and for the test, are you gonna be asking for the force diagram?
On this particular quiz, I don't, but it's generally a good idea in terms of showing your work.
So just to show you just to tell you how we're thinking?
Yes.
Okay.
Because if the force diagram's off, then the rest of it's gonna be off. So it gives me some sort of idea of where you're coming from. Other questions from chapter 4 homework? All right, I'd say let's just get this quiz done. We do have the option of just letting it record, which is always exciting to watch. But I'm gonna pause it. We'll start out with, so I got the recording part done. Any questions? Besides those. Okay, then let's pick up sort of where we left off. So this is the banked road problem. So you're going around a curve and the road is not flat. So there's an angle to it, which is known as a bank. So overhead view, cars going this way. That's the direction of the velocity. And then from a rear view or back view, you're looking at the car going away from you. With the slick profile of a rectangle. It's a scion. So, force diagram. We're going to go through the exact same process that we've gone through so many times. But if you haven't dreamt about it yet, you haven't done it enough. All right, so what are the forces acting on the car?
Yeah. have gravity that's acting down on,
What's that?
we have weight acting down on the car and
Okay.
on the bank. Well,
Okay.
yeah, on the bank. Is the bank part of the ground?
I assume so.
Okay. And we've already determined the direction of the acceleration, right? That was like our,
That was meant to be the cliffhanger, but, yes.
right?
So, is that the only force acting on it?
No. There's normal force, which is acting up on the car, down on the ground.
What does normal mean?
That means, it's
Why?
perpendicular to the surface.
Yeah, normal means perpendicular. So it's gonna be that way.
Oh, stop.
And that way. Not worried about friction right now because there's really, there's not enough information to know what the friction is. So typically in a bank problem, you need to solve the ideal case first unless you're told explicitly more information, such as which way the car wants to slide. So basically it's gonna take the curve, and if it's going just the right speed, it's gonna take the whole curve without moving up the track or down the track. So direction of acceleration,
It's to go up, yeah.
and so we set up our coordinate axes. So we've done the force diagram, direction of acceleration, coordinate axes, and so one of them in the direction of the acceleration, and the other one perpendicular to that, up or down.
Up.
So what are we breaking up? We're at the decomposition phase,
Normal force?
okay? Because weight is in the negative j hat direction, so we don't have to do anything with that. But y is off in whatever quadrant that would be called. So, a little geometry here. I know this angle here, theta, y is perpendicular to that. So that is a right angle there. I know that angle there is theta. Therefore, this angle right here must be the complement of theta. And so as I break y up, this angle up here must be theta. Because this is theta prime. And so this becomes y sine of theta to the left, y cosine theta up. So we're left with our force diagram of y cosine theta up, weight down, and towards the middle, y sine theta. So decomposition equations of motion. How many equations will there be?
2.
And what are they?
I hat and J hat.
Okay. Narrowing that down a little bit more.
You want y cosine.
Theta minus the weight is equal to,
M2 of gravity.
M2 of gravity is what I heard.
The acceleration due to gravity.
Why?
Or no, it's the acceleration, my bad.
Okay.
Y is because that's what it's always equal to.
Okay, so what is the acceleration?
We don't know, that's what we're.
Oh, we do.
We do? Oh, it's 0, because it's,
Yes.
there's no vertical.
Yeah, again, we chose the direction perpendicular to acceleration, better have the acceleration equal to 0. So mass times 0. And then the other equation?
y sine of theta is equal to, mass, wait. Do we need a subscript there?
There's only one mass, so.
We even have the mass we have on
And then our acceleration, which is,
that. Don't know, right?
yeah, right, I don't know.
But we did know one thing about this acceleration.
Wait, now it's in this direction.
That, okay, 2 things then.
It's gonna be, no, never mind. I don't know.
What's causing this acceleration? Change that slightly. Remember, acceleration is, there's 3 things that can happen which tells us there's acceleration. think back to, what are the three accelerators in the car?
The gas,
Okay, that's one.
Yeah.
friction,
Direction.
or change
All right,
direction.
jumping back to the original question. Yes, change in direction. This acceleration is caused by change in direction. The three accelerators in the car: gas pedal, brake pedal, steering wheel. Because this acceleration is from change in direction, it is centripetal acceleration. That's critical for when we do the substitution phase. Because ultimately, the question is asking for the speed. V typically doesn't show up in this unless there's centripetal motion going on. All right, substitution phase. We have a formula for weight. We have a formula for centripetal acceleration. So y cosine theta is equal to mg, by bringing that over and substituting. And then y sine theta equals mv squared over r.
Is the formula for centripetal acceleration just v squared over r, and then you just add the m?
Yeah, v squared over r is the, yes.
Okay.
I do have a question.
Yes.
This may be a bad time to ask it, but y is equal to mass times acceleration due to gravity, right?
No.
No? Y is just y.
Y is the normal force, whatever it happens to be equal depends upon the situation.
So what if we don't know it and,
Then we're either gonna solve for it or cancel it out.
okay. So like for cosine of y, oh my gosh. So like y, if y was minus cosine of theta for the top one, we would just say that the right is equal to 0, and then we add weight to the right side, and then y would be equal to the weight. You know what I'm saying?
I think so, but I'm not 100% sure. So
Yeah.
you're talking about if we had chosen down to be positive?
No, like y. Y by itself, not cosine theta, but weight would be cosine theta.
Oh, break it up like the box on ramp problem?
Yeah. I was doing one where it was, what is the normal force or something like that, and it was basically like, or what was the net force into the ramp, and I was confused because I saw in a video we did y is equal to mass times acceleration due to gravity, and I didn't know if that was just
Okay, so
y equals weight or.
box on ground, we have weight acting down, normal force acting up. Assuming that this box is not accelerating up or down,
Yeah. They're
y
the
is
same.
equal to, y, technically y minus w, let's make up positive. Y minus w is equal to 0, so y is equal to mg in that case.
Mhm.
If we do box on ramp, so we're not dealing centripetal motion, we're just dealing, put a box on a ramp,
Okay.
it wants to slide down the ramp. If we look at the forces acting on the box, we have weight acting down, normal force acting that way. In this particular case, acceleration would be down the ramp if there is any. So we set up a coordinate system like that, which means we have to break weight up.
Right.
And so weight, and so that becomes mg sine theta down the ramp,
Yep.
mg cosine theta into the ramp, as you know, in which case y minus mg or w cosine theta is equal to 0, so the normal force is equal to mg cosine theta.
Okay.
In this particular case, because acceleration is not down the ramp, there is some acceleration, we break it up differently, so now y cosine theta is equal to the weight.
Okay. Okay.
I did sort of a scatter shot there, I
No,
don't know if
you're-
I really addressed what the issue was.
You're good. I was just curious about the y equaling mg because it just confused me. Like I was thinking about it, and I guess weight and mg are the same thing.
Yes.
But for this problem, I was confused when you said acceleration isn't down the ramp. The acceleration would be to the left, so it changes.
Yeah, and very much. Unfortunately, we don't have, or fortunately, for whatever reason, fortunate or not, there's not a formula for normal force. It really is problem specific. Just like tension, there's not a formula for tension.
Okay.
And if you then try to go through, one of my hesitations of doing this like this is I don't want you to think, ooh, normal force is vertical, therefore y equals mg. That, no, because I can change this so that it's not equal to mg,
Okay.
which I think is, there's one of the, I think one of the master set problems, I have a rope pulling on it, up at an angle, in which case the normal force is not equal to the weight. Right. Are you feeling
Yeah.
good enough?
Yeah. That, perfect.
All right, so now our two unknowns are V and Y. Let's go ahead and make this Earth. Generic place on Earth. Two equations, two unknowns. You can solve for y and substitute into the other one, or since ultimately we're trying to find v, let's get rid of y. I'm gonna do it with a division, so I'm gonna do this divided by that, so I'm gonna divide the left side by y cosine theta, and divide this side by mg. And I'm left with tangent of theta equals, masses cancel out, v squared over gr. So v is the square root of gr tan theta. Questions there before we do plug and chug?
The R comes from our formula of centripetal